Okay, we are in the process of finding the limit as x goes to negative infinity, infinity, and then looking for the existence of horizontal asymptotes. So just real quickly, when we find the limit as x goes to plus or minus infinity, we're analyzing the what of the graph? What do we call it? The end behavior, very good. The end behavior. And there's only a limited number of things that a graph can do. It can increase without bound, it can decrease without bound, it can oscillate between two values, or it can taper off. And if it does taper off, remember, we say we have a horizontal asymptote at that value. So very quickly on part D from yesterday, when we were going to infinity or negative infinity, we first of all have to find the terms in the top and bottom that are the leading terms. And those are the ones that have the largest power. Everything else is essentially insignificant in terms of what's going to happen in the long run. Then you analyze how fast the top grows with respect to the bottom. So on part D, because it was x squared in the bottom and x to the first and top, anything that's squared grows faster than anything that's to the first power. So anytime the denominator grows faster by any amount, x to the first and the top over x cubed, or x to the first over x to the fifth, you're always going to get your ratios getting smaller and smaller in magnitude, approaching zero. Okay, and it might approach zero from above or below depending on which side you go, but there's always a horizontal asymptote at zero, and it affects the graph on both ends. The second case was part E, where we had x squared over x squared. So now they're growing essentially at the same rate, and anytime they're growing at the same rate, x squared over x squared, or x cubed over x squared, cubed, it's going to be the leading coefficient over the leading coefficient. And there'll always be a horizontal asymptote at that number. And for a rational function like this, a quotient of two polynomials, it'll be the same on both sides. The graph is going to be approaching the same number on both ends. And so that brings us to case 3 this morning, to part F. If you identify the leading term in the top, it's 4x to the fifth, and at the bottom it's negative 6x to the fourth. So in this case now, the top has a larger exponent, so the top grows faster. So what happens to a ratio when the numerator grows faster than the denominator? If you look at some values, let's look at like 10 over 1, 100 over 2, 1,000 over 3, 10,000 over 4. If you look at the sequence here, both the numerator and the denominator are getting bigger, right? But the numerator is getting bigger a lot faster than the denominator. What's happening to these values? They're getting bigger. They're approaching some kind of infinity, plus or minus. So anytime the top is greater than the bottom in degree, regardless of how much bigger, here the difference is only 1. It could have been x to the 6th over x to the 4th, whatever. You know that your two end behaviors are some type of infinity. So I'm going to put down infinity and come back and get the sign, and then you would have no horizontal asymptotes. Now, how are you going to figure out which type of infinity it goes to? You got a 50-50 shot if you guess. Is that what we're going to do? Pretty good odds, right? We want better odds. We want 100% odds. So all you have to do to figure out what type of infinity it's going to is plug in the representative type of infinity you're approaching. So as you go to the right, you're going to be plugging in larger and larger positive values. So if you, again, disregard everything but the leading terms, plug in a positive number into your leading terms and see what you get. 4 times positive to the fifth is what? 4 times positive to the fifth is a positive number, right? But in the bottom, positive to the fourth is positive times negative 6. That's negative. So the top will always be positive, and the bottom will always be negative. And what's a positive divided by a negative? Negative infinity. So you're plugging in to get the SIGN sign. And now when you go to negative infinity, just do the analysis all over again. When you plug a negative number into the leading terms, in the top you're going to get negative to the fifth, which is negative, times positive 4 is negative. So you get a negative in the numerator now. And in the bottom, negative to the fourth is positive, times the negative 6 makes it negative again. What's a negative divided by a negative? A positive. So you get either plus sign infinity, or of course, you don't have to write anything at all. So that's how you can get, that's one way to get the sign of the infinity. The other way to get the sign is to just simplify your leading terms, kind of like we did over here. The x squareds divide out, and we're left with 4/3. If you simplify your leading terms, you get 4x to the fifth over negative 6x to the fourth. If you simplified that, you're going to get negative 2/3 x to the first. And what would the graph of negative 2/3 x to the first look like? Think back to Algebra 1, right? It's x to the first, so it's going to be a line with a slope that is negative. So it's going to look something like that. We call that the end behavior model. End behavior model. If you were to look at this graph with all of the terms in it, then locally it's going to have some pretty interesting stuff. It could have like 4 discontinuities, x-intercepts, y-intercepts, turning points. But if you zoomed out on that graph and you looked at it from outer space, you're not going to see all the local behavior any more than when you zoom out on a Google Earth from New Braunfels, you don't see the town square eventually. It goes away and you just see, the end trends. So that's why we call it the end behavior model. If you were to zoom out on the graph, it would start looking more and more like the line that is negative 2/3 x. And because the line, as you go out to the right, goes down to negative infinity, so does the function. And because the end behavior model, as you go out to the left, goes up to positive infinity, so does the end behavior function. Okay, so that's why we call it the end behavior model. It's not the same function, but it has the exact same end behavior. And you can get it by simplifying the leading terms. So that's the other way to do it. Either know the top grows bigger faster and it's some type of infinity, then step 2, come back and get the sign, or look at the end behavior model. So those are your 3 cases, and you need to kind of just have them, commit them to memory. All right, so let's do it one more time. Anytime the bottom grows faster than the top, what's the limit as x goes to plus or minus infinity? 0, always, regardless of how faster it grows in the bottom. If it grows faster in the bottom than the top, it's always 0. If they grow at the same rate, x squared over x squared, x to the 10th over x to the 10th, it's leading coefficient over leading coefficient. And those are the 2 cases where you're going to get a horizontal asymptote. One's always at 0, the other is also always at leading coefficient over leading coefficient. And then the third case is when the top grows faster by any amount, it's going to be some type of infinity, and then there is no horizontal asymptote. Okay? So let's put it all together here. This is reading mathematical sentences and trying to construct a graph based upon it. So let's draw the graph of a function f of x on the interval from -5 inclusive all the way to infinity with the following characteristics. Okay? So let's go ahead and give ourselves a palette on which to draw. And that just means let's give ourselves an x and y axis. All right, so reading the first thing right here. It says the limit as x goes to -3 from the left is -2, which happens to also be the function value at -3. So if you think about what's happening, at -3 we have the road coming in from the left equal to the bridge. And they're meeting at -3, -2. So I'm going to come over here to my graph, and I'm just going to call this right here arbitrarily -3, and I'm going to call this -2. Maybe I'll label the -3 up above here. And I'm going to put a solid dot. Why a solid dot? Because it says right there f of -3 is -2, and that's also the limit as you approach from the left. So I'm just going to kind of draw a line coming in like that for now. I'll maybe change it later, depending on what other requirements I need. Okay, so just a little mark to show that it comes in from the left and dives into that little dot there. Now the next piece, as we approach -3 from the right-hand side, from the other side of -3, the y values are approaching infinity. What graphical feature must live there then that would force the y values up to infinity or down to -infinity at a specific x value and not at the end of the graph? Vertical asymptote. Sweet. So that's what that means. There's a vertical asymptote at -3. So I'm going to go ahead and draw a dotted line. And you can actually have a dot on a vertical asymptote. By way of a piecewise definition, you can explicitly define it to be a dot. So as I approach it from the right-hand side, I need to go up to positive infinity. So I'm just going to draw a little piece of the graph like that. And I'll finish it out later on. All right, so that takes care of the first 2 things. Now it says f of 0 equals 0, which that's the y value. That means the graph has to pass through the origin, right? So I'm going to put a solid dot at 0, 0. And it also says that that's the limit as x goes to 0. So would that be from the left or from the right? Or both? If it's the general limit without the plus or minus on the 0, it means from both sides, right? So I know it has to be approaching 0 from both sides. So thinking about what's happening at -3, maybe I'll kind of draw it like that and draw it like that. And I'll fill in later. Okay, that's the trend that I need to make happen. All right, so I meet that requirement, so I cross that out. Now it says as I approach 3 from the left, I'm approaching 4. So let's call this right here 3. As I approach it from the left, I'm approaching 4. All right, so I'm just going to draw a little line kind of going up there. I don't know right now. I'll put an open circle because it doesn't say anything yet about what's happening at the 0.34. That's just the limit from the left. So I got that taken care of. And now it says when I approach 3 from the right, it equals 1. So if I call this value 1, as it comes in from the right, it's got to be approaching 1. So I'll put another open circle. And again, I have it drawing it coming in from the top. You can have it easily, just as easily coming in from the bottom like that if you want. Whatever. Answers will vary. And then it says right here, f of 3 is -1. So notice I didn't fill in any of those dots because I wasn't sure where it was going to be defined. Now I can clearly see that it's going to be right here at -1. So I'll put a solid dot right below the x-axis, right above the 3. And then the last piece, the limit as x goes to infinity has to equal 2. So I'm going to just say 2 is right there. What graphical feature then must live there if the end behavior approaches a finite y value? A horizontal asymptote. Okay, so now all I got to do is fill in on either side of each of these x values where the behavior was given. And you could be as creative as you want as long as your graph passes the, what? Vertical line test. Yeah. So I'm going to have this one, instead of going up, I'll make it do a little bit of dancing. Why not? This guy here, I'll just connect it since I already have it drawn. That's easy enough. From here, I'll just, maybe I'll kind of trim some of this back and just kind of have it turning like that. And now since I changed mine to go down, I will have to turn around somewhere and approach the horizontal asymptote. But you know what? I'm going to be crazy today. I'm actually going to cross it and approach it from above. Is that legal? Can a graph cross its horizontal asymptote? Sure. So the only thing that matters is if I got the behaviors correct on the specific values of x that were given. Other than that, you can fill in with pretty much anything. And so when there's one on the worksheet like this, I kind of expect to see a lot of different graphs when y'all turn them in. It's very unlikely that y'all will be thinking the same thing. So kind of get creative, kind of get clever, just to make sure it passes the vertical line test. If you like your graphs extra holy, you can actually just put a bunch of holes in it if you want. Maybe you even put another vertical asymptote here, right? As long as you met the requirements that I gave you, the rest is entirely up to you. So play around, and then you're not working, you're playing. So there you go. That's how you transcribe. Oops, I did forget one thing here, and I'm glad I kind of came back. What does it tell us right there? That my graph only lives where? Between -5 and infinity. So I kind of got carried away over here on the left at the end. I can only go as far left as what number now? -5, yeah. So that was a very important little piece. That was a close call. So I'm going to go ahead and call this -5. And you know what I'm going to do? I'm going to just say there's another vertical asymptote right here at -5. And instead of going up to infinity, I'm just going to curve it down. Yeah, crazy with a capital K. I know. Uh-oh. Does that still meet the requirement? This says -5 greater than or what? Equal to. Do I have the function existing at -5 now? No. So guess what I'll do? I'll just put a dot somewhere right here on the vertical asymptote. So this would be like an ugly piecewise function. If you're going to be writing the equation of this, you would have one of those funky braces, and you would have a lot of different pieces. It would be very difficult to come up with the equations that generate the graph. But if you're drawing a graph, it's a lot easier, right? Because the only rule is pass the vertical line test, and you got it. Okay, so there you go. Now I think we've met all the requirements, and we're done with that, putting it all together. Any questions on that one? We got one page left, and we got about 19 minutes in which to do that. So I think we're making good time. Summary. Okay, here we go. If the limit as x goes to c from the left equals f of c, which equals the limit as x goes to c from the right, then what could be said about the function f of x at x equals c? Yes, very good. We could then say that f of x is continuous at x equals c. This will be the road coming in from the left, equaling the bridge, equaling the road going out on the right, or coming in from the right, if you want to think about it that way. F is continuous at c. And it's important now that we understand what the limit is, because it becomes part of the definition then of every discontinuity, every asymptote, and it's so important in the definition of continuity at a point. All right, number 2, if the limit as x goes to c from the left equals the limit as x goes to c from the right, then what can we say about the general limit as x goes to c? Can we say anything about this on the end? If the limit from the left equals the limit from the right? Does it exist or not exist? It exists, right? So without having any value, we could just say that it exists. If you want to kind of amend this and you want to say that this equals L, usually we call it L for limit. I'm going to use the Laverne and Shirley script letter L. That's kind of a cool L. The capital cursive L, kind of a cool thing to make. If we say that that y value then is L, then not only does the general limit exist, but it's equal to L as well. It's fun to use cursive. It's like you're drawing letters instead of writing. Nice. Okay. Number 3, if the limit as x goes to c from the left ain't equal to the limit as you approach c from the right-hand side, regardless of what the function value is doing at c, then f has what type of discontinuity at x equals c? Jump. F would have a jump at x equals c. And again, f of c could be anything or nothing at all. The jump discontinuity does not care about where the dot may or may not be. If the two roads are not lining up, you have a jump. Number 4, if the limit as you approach c from the left equals the limit as you approach c from the right, but that does not equal the function value, either because the function value is somewhere else or it doesn't exist, then f has what type of discontinuity? Whole. Good. We're going to have f has a whole at, now let's go ahead and do what we did up here. Let's say that the two one-side limits equal L again, which is a finite y value. Then we could say that the function has a whole at the point c comma L. Remember, the y value of the whole is not the function value. If it were, it would be continuous. So we don't care about the function value again for a whole as long as it doesn't plug the hole. That's the only thing that matters. If it plugs the hole, we don't have a hole, right? How much dirt is in a hole 3 feet deep by 2 feet wide? None, right? It's a hole. Good. Number 5. If the limit as x goes to c from the left is infinity, or the limit as c goes from the, this should be a plus sign there if you want to add a little plus sign, or the limit as x goes to c from the right, oh, actually it's not. It's not. I'm just getting tunnel vision here with the iPad. It happens sometimes. If we approach c from the left, and we either get a positive or a negative infinity, or we approach c from the right-hand side, and similarly we get positive or negative infinity, what feature does the graph have at x equals c? Vertical asymptote. Good. F has a VA at x equals c. Now, there are some functions that only live on one side of their vertical asymptote. Let me kind of throw this parent function at you. Let's call it f of x equals ln of x. Have y'all seen that before, ln of x? Have y'all studied logs before, log functions in Algebra 2? Yeah. ln of x we call the natural log, and we're going to be studying that in a later section exclusively. This is equivalent to log base e. Log base e, what the heck is e? E is called the natural base. It's the second most famous irrational number in all of mathematics behind pi. It's about 2.718 ... It's called the natural base. So when you see ln of x, we read that as the natural log of x. It's really log base e. This is a logarithmic growth function. And don't worry now if you don't get this. We're going to be studying logs in an entire section later on. But logs have a vertical asymptote on the y-axis, and if it's a base that's greater than 1, like log base 10 or log base e, it looks like that. They cross at 1, 0. So there is a function that has a vertical asymptote, but it only lives on one side of its vertical asymptote. What would the limit be as x goes to 1 from the left-hand side of the natural log of x? Based upon the, oh, I'm sorry, not 1, my bad, 0. What would the limit be as we approach 0 from the left-hand side? Can we approach 0 from the left-hand side? Is there a road that we can even hop onto and start heading back? No. So much like the radical function we saw yesterday, this limit is dne because there's no graph there. And if there's no graph there, there's no point there. And if there's no point there, there's no point in doing it, right? And then what would be the limit as x goes to 0 from the right-hand side on the natural log of x? Well, now you can hop on the graph and start heading toward, you're going down, 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 which is negative infinity. Which means that the limit doesn't exist because it decreases without bound. So there are functions out there that you can define with a single piece that only live on one side of the vertical asymptote. But most graphs, most rational functions live on both sides of the vertical asymptote. All right, and the last one here, if the limit as x goes to positive infinity exists and is equal to L, or the negative infinity exists and is equal to L, I'll call this L1 and L2 because they don't necessarily have to be the same value. Then what graphical feature does the graph of f have as a result? What do we say? F has a, if I go out to the right and I taper off towards a specific y value, that's what that's saying. I have a horizontal good asymptote at y equals L or L1 and y equals L2. So most functions have that have a horizontal asymptote, rational functions, it's going to be affected by the horizontal asymptote on both ends, like we did up here. This graph is going to 0 on both sides, on both ends. This one's going to 4/3 on both ends. Let's look at an example, though, of some other functions. If you just look at y equals e to the x, what type of function is y equals e to the x, or y equals 2 to the x, or y equals 5 to the x? When the variable is in the exponent, this is called an exponential function. And we're going to study exponential functions later on, right before we study log functions. So the base e is still 2.718, so this would be exponential growth. And here's what the function of any exponential growth function looks like of the form b to the x. As long as b is greater than 1, it's going to be growth. It looks like this. It comes from the x-axis, and then it gets really big really fast. So here's the end behavior. The limit as x goes to infinity of e to the x is what? What's the right end behavior of this green graph? Hop on the graph, start going out to the right. What are the y values doing? They're going to infinity, right? They're going up. They're increasing without bound. Well, what's the limit now as x goes to negative infinity on the graph of e to the x? 0, yeah. So here is a function that has a horizontal asymptote, but it's only affecting the graph on one side and not on both sides. Then you have a function like this. You don't know what this is yet. We're going to study trig in the second semester. But there is a function out there called arctangent of x. And I might as well just throw them at you right now. You're going to be responsible for them later on. But he looks like this. He has a horizontal asymptote at y equals pi halves. And he has another horizontal asymptote, a different one, at y equals negative pi halves. And what it looks like is this. Oops. Let me draw that again. It goes right through the origin. And it has what we call origin symmetry. It's rotationally symmetric. If you flip it around 180 degrees with your finger on the origin, it looks exactly the same. Let's look at the limit as x goes to infinity then of arctangent of x, and the limit as x goes to negative infinity of arctangent of x. All right, what's the first one? As you hop on the graph and go out to the right, you're getting closer and closer to pi halves, right? And as you hop on the graph and go out to the left, you're getting closer and closer to negative pi halves. So there's an example of a function that has two different end behaviors, but it's still tapering off on both sides to what becomes two different horizontal asymptotes. Can a function have three horizontal asymptotes? How many ends are there on a graph at most? Two, the left end and the right end. So the maximum number of horizontal asymptotes a graph can possibly have is in fact two. If you wanted to give another horizontal asymptote, because there is a graph of a function called inverse tangent that's not really a function at all, there would be another horizontal asymptote up here at 3 pi halves. But is that a function anymore? No, that fails to be a function now because it fails the vertical line test. So any function can have at most two horizontal asymptotes. So there's kind of a nice little catalog of some examples of functions that behave kind of uniquely on their ends and around the vertical asymptotes. But that's it. That's it. Do y'all have any questions on 2.2? I have a pretty good idea of what a limit is, right? The limit is a y value, but it's not the y value that we go to and stand on. It's the y value that we approach. And it's important to know what the limit is because we define continuity and discontinuities and asymptotes in terms of limits. All right.